So here we are, we're going to start talking about organic compounds now. We've talked about a lot of general things about compounds. Now we're going to get specific, simply because organic compounds are kind of special, at least in Joel's minds. But anyway, what are organic compounds? Well, they're compounds that contain carbon, you would tell me. And that's kind of right, but it's not completely right, because, for example, carbon dioxide contains carbon and it's not organic. Sodium carbonate, Na2CO3, contains carbon and it's not organic. So it's not enough just to say they contain carbon. They must have a bond between a carbon and a hydrogen atom, or really just to incorporate 3 or 4 extra special compounds. Instead of a hydrogen, it can be a halogen. So for example, carbon tetrachloride, CCl4, is considered to be an organic compound because that halogen, the chlorine, is equivalent to the hydrogen in that definition. Now, every organic compound has got 2 bits to it. There's the single bonded carbon-hydrogen bit, the hydrocarbon, the bit that comes from alkanes, as you might remember from your previous studies. And then there's the interesting bit, the so-called functional group. So if we think of ethanol, for example, there's the structure of ethanol. The circled in green there, the C2H5, well, that's the boring, unreactive alkyl part, but then the bit in blue there, the alcohol, is the functional group. That's the fun bit. That's the thing that does everything, including the reactions. However, something that we'll focus on during particular parts of this course, more so than you would have done at A level, is that we do also have to think about the boring, horrible bit, the hydrocarbon bit, because that can affect the products depending upon how big it is and the general nature that it has. Now, during the course of this part of the module, we're not going to do any reactions. That's all saved for the next module, chemical reactions. But we are going to think an awful lot about the different structures of organic chemistry compounds. We're going to think about, in particular, the alkyl part of it. And we are, of course, at some point going to talk a little bit about how we name those. And of course, ethanol here, you can see you've got the green bit there. That's the boring bit. Arguably, the an bit is also the boring bit. And then the ol is what tells us that it's fun and all about an alcohol. So what's so special about carbon? Why are there 10 or so times as many compounds that contain carbon as compounds that don't contain carbon? Well, there's several answers to that. The most important one of which is that, of course, it makes 4 bonds, and those bonds are generally strong bonds. If we look at this rather muddled picture here that shows bond energy going up the vertical axis, so that's really the important thing. And then you've got bonds between the various atoms down here. So for example, carbon is in this orangey color here, and so here's the orange one. So the bond between carbon and hydrogen is a smidge over 400. The bond between carbon and carbon itself right there, about 350. Okay, and so on. So if we trace along that orange line there, we can see that the bulk of the bonds that carbon makes, a little exception here for phosphorus and sulfur, although still nice and strong, but just about all the bonds that it makes are over 300 kilojoules per mole, and that's a pretty good strong bond. Okay, so if you're going to bond to carbon, it's probably going to be a strong bond. Now, even more significant is that carbon really bonds nice and strongly to itself. Right, there's that little circle there. There's pointed out earlier about 350. What that means is that it's very, very easy for carbon to make lots of chains of carbon atoms, rings of carbon atoms, and of course you're familiar with those from your previous studies. Now, if we consider the other second period P block, so we'll go from carbon to nitrogen to oxygen. Okay, the bonds between nitrogen and nitrogen right down there, very, very weak. Oxygen to oxygen, even weaker. Fluorine to fluorine, a little bit stronger than the oxygen to oxygen, but nothing to shout home about. And so these nice atoms here that you might say, well, if carbon's sort of in the right period and everything to do all this nice bonding to itself and so on, why won't nitrogen, oxygen and fluorine do it? And of course, the answer that you might remember from when we talked about bond lengths is that these bonds are weaker than they should be because of the lone pair repulsions. Nitrogen's got 1 lone pair on each repelling each other, oxygen's got 2 lone pairs on each oxygen atom repelling, and fluorine has 3. Now, of course, those of you who are science fiction buffs will think, well, now there's that whole wonderful thing about if life can be based on carbon, why can't we also have life based on silicon? Why aren't there tons of silicon chains and rings and so on? And as we'll actually talk about next term in main group, there are a few compounds known of silicon analogous to the alkanes, but not very many, because if we look at silicon, right, silicon is the yellow line here, and the bond between silicon and itself right there is very weak too, comparatively, just over 200 kilojoules per mole. No lone pairs there to repel them, but still significantly weaker than the carbon-carbon bond. So the main reason why carbon is so prevalent, why there are so many millions of organic compounds, is that strong bond length of carbon to itself, also to hydrogen, and also to oxygen and fluorine and these other heteroatoms. Now, it's important to point out that these are not just 4 strong bonds, but they are 4 strong covalent bonds. Okay, now of course when you think about ionic bonds are nice and strong as well, but ionic bonds sort of are they're essentially, you think of them as attractions between a positive sphere and a negative sphere, so they're not very directional at all. Although we'll talk about the structures that ionic compounds have in the solid state again next term quite a bit. But the fact that carbon has these strong covalent bonds that can just go on and on and on and on is a very significant reason why there are so many millions of organic compounds. And we can illustrate this by casting our thoughts back to what we talked about a couple of weeks ago with periodic properties. If we think first of all about cations, okay, well of course you're very familiar with your lithium, sodium, potassium cations, and it only takes 400, 500, 520 kilojoules per mole to pull that electron away. Remember, making cations is always endothermic. It always requires energy to pull the electrons away. But, 500 odd kilojoules per mole, that's not much between friends when you are making those ions. Now, of course, we go up to the alkaline earths, and there we're trying to make 2+. And so we got to pull away both the first and the second electron. And you can see that these are quite a bit stronger, as you would expect. It takes a bit more energy to remove the second electron than it does the first electron. And so to make 2+ ions, you're up there around 2,000 kilojoules per mole for magnesium and calcium, close to 3,000 kilojoules per mole for beryllium, which is one reason, as we'll talk about again, guess what, in next semester, why beryllium compounds are so fascinating. Let's go a little bit further. Aluminium and gallium are 3+, so we've got to have the first electron and the second and the third electrons pulled away. And when we add those up, we're over 5,000 kilojoules per mole in order to make those ions. And so, yes, there are some 3+ aluminium ionic compounds and some 3+ gallium compounds, but not nearly as prevalent as the calcium and the magnesium ionic compounds when it's just 2+. So to remove yet another electron to make carbon 4+ would take a whole heck of a lot, nearly 15,000 kilojoules per mole. You're not going to make carbon 4+ cation. Well, how about the anion? Okay, if we think about what the anion of carbon would be, we would expect it to be C4-. Now, if you think back to our electron affinities, most electron affinities are exothermic for putting one electron into an atom. Now, so there we are, fluorine -328, chlorine higher than fluorine, which is of course an anomaly, but that's because fluorine is so small, as we talked about with electron affinities, and there's bromine as well. So kind of easy to get an electron into your halogen atoms, so that's why the halide anion is very, very prevalent. How about sticking in a second electron, as we would have if we made oxide or sulfide, O2- or S2-. We might remember from our discussion about electron affinities that while most of the first electron affinities are exothermic, in other words, energy is given off when these atoms acquire an extra electron, to then try and stick a second electron into an atom that's already 1- requires you to put energy in. So second electron affinities are endothermic. And then, of course, you'd expect third ones to be even more endothermic. So to make N3 plus requires 1750 kilojoules per mole, right, to stick those 3 electrons in. So again, you can imagine what it would take to throw a 4th electron into carbon. Fortunately, I can actually find the 4th electron affinity of carbon, but when you add up the 1st, the 2nd, and the 3rd, and then you imagine what the 4th is going to be even more endothermic, it would take way over 3000 kilojoules per mole to make the C4 minus anion. So again, those bonds are not just good and strong, but they are covalent bonds, which allows those molecules to form nicely. Of course, anytime we talk about covalent versus ionic, we have to think about electronegativity. Carbon right there has got a sort of middle electronegativity in terms of the non-metal atoms, so it's going to be quite happy to form covalent bonds to all of those. And finally, carbon doesn't just make good, strong single covalent bonds, but we also have, as I'm sure you remember from your previous studies, the possibility of multiple bonds. So if we look at these, carbon can form double bonds, but double bond to itself, rather strong bond energy there. And in comparison, nitrogen double bond to itself and even oxygen double bond to itself in O2. Much weaker double bonds, again, because of those lone pairs there. Carbon can, of course, form triple bonds to itself. Well, the only analogous molecule that's made up of a triple bond, 2 atoms triple bonded to each other, is N2, and that has a higher bond energy, but of course N2 is an extremely stable molecule, and as we'll talk about when we get into thermodynamics, you like compounds with nitrogen in them to make explosives, because when they make that N triple bond N, you get a whole bunch of energy coming out. Carbon can't just multiple bond to itself, but it double and triple bonds to nitrogen, and it double and triple bonds to carbon as well. And you can see these really nice strong bond energies there, 615 for the carbon to nitrogen double bond, 800 for the carbon to oxygen double bond. And of course, when we talk about infrared spectroscopy, we talk about the significance of that very strong bond there as well. So why are there so many organic compounds? Because carbon is special. It's small. It forms very strong covalent bonds, so it can form rings and chains with itself, and not just single bonds with itself and other atoms, but double and even triple bonds. Carbon is, much as I hate to admit it, a very special, unique atom.